CAM's presentation for the preliminary design report. This is, like I said, for the other section, this is my first time teaching preliminary design of Dr. Martin. I forgot to introduce myself. So if they screw up, it's really my fault, not theirs. So just want to take the pressure off the team. But anyways, I will let you guys go ahead and go for it.
Thank you, Dr. Martin. So hello, everybody. Good morning. My name is Daniela Baroni. I'm the team lead for Project CAM, which stands for Camera Attachment Mechanism. And with me are Sean Rager, Philip Outzman, Aiden Moore, Brian Bertucci, Alex Liviars, and Sean Prendergast. And today we're going to be discussing the preliminary design of our system, which we refer to as CAM. And in our presentation, we're going to talk about the purpose of our project, the objectives and the concept of operations, the system level requirements, and subsystem level requirements, and wrap it up with lessons learned and conclusion. So the purpose of Project CAM is to participate in the Micro-G Next competition that is sponsored by the Neutral Buoyancy Lab at Johnson Space Center, where the participants, as shown in the image on the left, is they get to travel to the Neutral Buoyancy Lab if they're chosen and be able to communicate with a professional diver who will test their system. As shown on the image on the right is an example of a diver performing a mission. And as of yesterday, Johnson Space Center has announced that Project CAM will be going to the Neutral Buoyancy Lab. And we're all very excited. It's a great time. So the challenge that we are particularly participating in is the EVA Camera Attachment Mechanism Challenge, hence the name, where we have to attach to different interfaces located on the exterior of the International Space Station. And the reason for this is because currently astronauts, as shown in the image on the left, have cameras attached to their helmets, where it provides a first-person view to mission control, but it's kind of limited when trying to communicate directions and making sure that the mission is progressing smoothly. And our solution to that is to create a mechanism that will attach to different interfaces similar to those located on the exterior of the ISS and will allow the astronaut to configure the position of the camera in different ways. And I will pass it off to Sean Rager to talk about our solar systems and system description.
Thank you, Daniela. So there are several similar systems that Project CAM drew inspiration from when we were designing the different components of our system. One of these was the UBC Universal Beam Mounting System. Now this is what drove some of the base design, as the beams that this attaches to are similar to the I-beam trusses that are on the ISS. Another inspiration was the GoPro monopod stick. Now this is inspiration for the ARM subsystem and is similar to our final design in the locking joints and the multiple arm linkages. Now the third similar system that we drew design from was a proposed gripper designed by NASA. Now this was proposed to grip onto the EVA handrails, which are one of the things that we have to attach to ourselves for the competition. So CAM's overall configuration allows for a long camera reach while also allowing the device to be compacted into a small space. Now CAM is comprised of four main components, namely the camera mount subsystem, the arm subsystem, the double ball joints, and the base subsystem. Now all four of these components do comprise the entirety of CAM, and when stored are in the configuration that you can see here. Now this size constraint was given to us by NASA. It is a 12-inch by 16-inch by 18-inch box that we have to fit CAM into. This is in direct correlation to the crew carry bag that you can see here on the left. Now this is something that's used on most EVA missions by NASA. This is to transport any components that are needed by the astronauts or any tools that are used on the outside of the space station. Now the overall configuration of CAM also allows it to be maneuvered into many different positions and angles. As shown here in this video, the camera mount can move through its own independent axes while all of the other components are maintained in position. Now the arm linkages are also able to move without moving any other components, and all of these can be adjusted while the base is firmly secured to the outside of the ISS. Now all of these components are manually adjustable. There are no outside electronics helping any of these components. The only electronics on CAM are the actual GoPro camera, and this is all due to the regulations set by NASA for the competition. So as you can see here, cam can be adjusted from its compacted state into a camera looking directly at the user or looking directly at any of the other components that it needs to for the EVA mission. So now I'm going to hand it off to Philip Elterman to talk about our objectives and our concepts of operations.
Thank you, Sean. So there are 3 primary objectives that we deem critical for successful testing. Our first primary objective is that cam shall be manually powered. We're going to use a system of springs and a one-handed mechanically assisted squeeze-to-release grip as seen in this image of the base. That is our one-handed grip, and as well as the spring circled in the red. We will also be using the springs for our handles that will allow us to manipulate our double ball joints. We also have a second primary objective, which is that cam shall pivot. We're going to use ball joints as shown in this image of the camera mount to help manipulate the overall system. And with these double ball joints, we will be able to manipulate the entire cam system to obtain the optimum camera angle. We also have a third primary objective, which is we shall attach 2 of the 3 interfaces as stated by the NASA Micro-G competition. The first one we'll be attaching to is the seated card handrail, and this is used to help astronauts carry tools during EVA missions, as well as EVA handrails, which helps astronauts move along the outside of the ISS. As shown in this image is an astronaut holding onto the seated cart, and attached to the seated cart is a EVA handrail, and these are the 2 primary spots that cam will attach to. We have a secondary objective, which is to attach to all 3 interfaces on the ISS, which is also stated by the NASA Micro-G competition. This also includes the I-beam, which is found on various locations of the ISS. Project CAM has a concept of operations for testing at the Neutral Buoyancy Lab. We will start by handing CAM to the diver, debriefing them on how CAM works, and show them any possible pinch points or other safety hazards that are associated with the device. The diver will then attach it to the EVA handrail, the truss, the seated cart, and then finally the diver will return CAM to the surface and give feedback on how CAM performed underwater. I'm now going to hand it off to Aiden Moore to talk about our critical requirements and design choices.
Thank you, Phil. All right, there are several critical requirements that the team had to adhere to when designing CAM. The first was the approved material. We had to choose a material that was from the NASA approved materials list. We went with aluminum 6061 for its high yield strength as well as lightweight properties. Next, we had to create a system that was less than 15 pounds. Currently, our design is at approximately 7 pounds. The total volume had to be less than 12 by 16 by 18 inches. Currently, our design in its compacted state, which you can see on the right on the screen, is at 10 by 11 by 14 inches. Drain holes. So each subsystem of CAM had to allow the free flow of water. Currently, the only drain holes that we have on the system are shown by an arrow, which are mainly for weight conservation, but they do allow the free flow of water. Manual power, as stated before, the entire system had to be manually powered. The 2 arrows are showing the base system, which is manually operated, as well as the double ball joints, which both have squeeze-release handles. Next, it had to be EVA operable, and that an astronaut had to be able to manipulate this device easily. As you can see, the handle on the base subsystem right there is fairly large and allows the astronaut to get his glove inside there and manipulate easily, as well as the handle on the double ball joint. So although all system level requirements are being met, we aim to improve the user safety by the minimization of pinch points. So the requirement specifically states the device shall cause no damage to any hardware or EVA glove. And highlighted in red is a potential pinch point that we've identified, and we plan to minimize that by enclosing it with plates so that you can't trap a finger or anything else inside that location. And next, I'm going to hand it off to Brian to talk about the base subsystem.
All right, thank you, Aiden. Going into the base subsystem, the base is going to be the primary means of attaching the overall system to the ISS, which is in direct fulfillment of our primary mission objective. The evolution of the base design was spurred basically off of our secondary mission objective of wanting to attach to all three interfaces. Our initial design went off of our trade studies, in that we wanted to keep the design as simple as possible, keep it manually powered. With this design, we had minimal moving parts. It was spring operated. Moving on through the competition, we received further details on the actual dimensions of the interfaces that we were intended to attach to. Additionally, we found the similar system of the tether attachment that was stated previously, which led to this design, giving us the ability to operate the system using one hand. It also gives us a mechanical advantage through the operation of the system to allow for the minimization of the spring constant, so that the EVA operable portion of the system is fulfilled, in that the astronaut doesn't have to squeeze the trigger as hard as he would for a straight spring system. From this design, we moved on to what is now our currently design, with only some small changes to allow for the rest of the subsystem requirements. These subsystem requirements include, again, manually powered. One of the big purposes of this system was for the entirety of it to be manually powered. I think we need some new batteries on the clicker. Too far. Thank you. Again, EVA operable, as previously mentioned, we have a mechanical advantage in the base subsystem, which allows for the reduction of the spring constant, making it easier to operate. Next. Weight. Each subsystem had its own weight requirement. The base subsystem had a weight requirement of 7.5 pounds. The entire system currently is under that weight limit, and the base itself is at approximately 2 pounds right now. The volume restriction, again, is specific to the base subsystem. We had a requirement of 6 by 8 by 18. Our current dimensions for the base subsystem are approximately 4 by 7.5 by 10. A 2-fault locking system. The NASA competition requires that the base have a secondary means of maintaining positive connection to each interface. For this, if the primary means of connection, the main spring itself, were to fail, this secondary system will prevent the handle from opening and thus releasing the interface. 2 of 3, this is the attachment to 2 of the 3 proposed interfaces. Again, we're intending to attach to all 3 interfaces. As you can see in the imagery, we have it designed specifically for the different geometries of the 3 interfaces. A tether attachment. NASA requires that any removable component of the device have a tether attachment to prevent it from becoming free-floating objects in space. As there are no specific removable components of CAM, the base itself will maintain the tether attachment point for the entire system. And lastly, no damage to the ISS. For this, again, our material was chosen given that it is going to be a similar material to the attachment interfaces, which will help prevent any kind of damage to the ISS. Additionally, any sharp edges or corners will be removed from any mating interfaces. We're also looking into potentially covering all mating surfaces in a plastic or rubber material to prevent a metal-on-metal contact with the ISS. Going back to our primary mission objectives, to attach to the 2 of 3 interfaces, we see animation of the base connecting to the handrail. You can see the specific geometry of the base was designed to connect directly to the ISS handrail. Similarly, we have it connecting to the CDCAR truss frame. You can also see the secondary locking system fall into place as it connects to each interface. Lastly, our secondary mission objective is currently not being met in that the geometry of the base interferes directly with the connection point to the truss frame. As we move on to our detailed design, this will be fixed or mitigated by adjusting the arm location on the base to a lower positioning on the claw mechanism itself, and thus prevent any kind of interference as shown here. Moving on, I'll hand it off to Alex Ovieres to go with the arm subsystem.
Thank you, Ryan. All right, so the ARM subsystem is the second subsystem of the CAM overall subsystem, excuse me. The ARM subsystem's main purpose is to link the base subsystem and the camera mount subsystem together. We do this by means of 3 double ball joints and 2 structural linkages. The image on the left shows the ARM subsystem isolated from the rest of the system, and the image on the right shows how the ARM system integrates with the full system. So the ARM subsystem was designed to fulfill specific design requirements, the first of which was the handle diameter. This is a design requirement that we implemented to ensure that the handles on the double ball joints would be easily usable by an astronaut wearing an EVA glove. We did this, people go back. So we did this by setting that design requirement to a handle diameter of 5 inches, and we fulfilled that requirement by designing the handle to be exactly 5 inches. The second design requirement that we fulfilled was the range of motion requirement. This ensures that the camera mount has at least 45 degrees of freedom of motion in all 3 dimensions. With this double ball joint design, you can see that in its most limited axis of direction, we achieve a range of motion of 22.5 degrees. When you take into account that this happens on both sides of the double ball joint, you get a maximum displacement of 45 degrees, thereby fulfilling this requirement. The next requirement we had to fulfill was the total weight needed to be less than 5 pounds for the ARM subsystem specifically. We currently come in at 2.1 pounds, so we fulfill this requirement. And the last is the extended length, less than 33 inches. This is another requirement that we implemented just to ensure that the total length of the arm would not be past arm's reach when totally extended. So as you can see in the graphic, we come in at 28 inches, measured from handle center to handle center. And that ensures that even when at maximum extension, the handles won't be out of reach, so you won't have to reach farther than you would have to adjust that. So most of the design from the ARM subsystem came in with the joint. This joint's the most important part of the ARM subsystem because it connects all of the systems together and is what ensures our requirement being fulfilled for pivoting. So the design started with these joints. These are some of the preliminary designs that we started with. These are all based on the lower order kinematic pairs. Via trade study, we found out that the double ball joint gave us the most degrees of freedom, so we adapted that design to our current design, which is this 2-plate design. Essentially how it works is that this outer plate is connected with this outer handle, and this inner handle is connected with this inner plate. Between these 2 handles is their spring, and when the handle is compressed, the handles will move together, thereby forcing the plates apart. These plates will force apart just enough to let a ball joint seated in this pocket rotate freely, but not enough to allow it to slip all the way through. So that is how that works, and then when the handle is released, the spring will force the plates together and lock the joint. Linkages were designed to allow multiple positional configurations. We ended up with 2 linkages providing the most range of motion with the least amount of length for the arm. So this gave us this current design. On the left, you can see that this is just a standard open configuration, and on the very right is shown the compressed store configuration. Again, at the bottom of the screen, you can see that the handles measured from center to center are 22.5 degrees, or 22.5. It's 22.5 inches. So the joints and linkages ensure range of motion and allow modular assembly. So going back to that range of motion requirement, essentially in the ball joint you have 3 degrees of freedom that you can rotate in. You can rotate in this roll axis, which with the ball joint is unlimited. You can rotate in this pitch axis, which with this ball joint is greater than 200 degrees. And then the most limited would be parallel to these plates, which is shown here. And that would be 22.5 degrees, which is the half of what we need to do. And then, again, considering on both sides of the joint, you're going to get that 45-degree range of motion. So the arm system was also designed to be lightweight and strong. Essentially what we did was we did a couple of structural testing to make sure that none of our components would bend or break during the forces we would expect to see during normal use. So to do this, we simulated a 20-pound force axially. Because this will be operating in a weightless environment, we didn't expect to see more than 20 pounds of force at any one given time. So just to ensure that nothing would bend or break, we did a structural force there. You can see the stress concentration building up at the stem of the ball joint. Similarly, you can see that on this test, which we included the plates in the test. And then on this test, we did a 40-pound or 20-pound force at a 45-degree angle from the plates to simulate the ball being forced through the plates. In all of these tests, the maximum yield stress we saw was 11% of the total yield stress of aluminum 6061. So we're nowhere close to bending or breaking any of our components, which is good news. All right, so from here I'm going to hand it off to Sean Prendergast to talk about the camera mount subsystem.
Thank you, Alex. Oops, sorry. All right, so the last subsystem we have is the camera mount subsystem. Thank you. This is by far the simplest subsystem in form and function. It consists of just, next slide please, just a ball joint and then a plate and a camera mount. Now, for the purposes of testing at the MBL, NASA is going to provide us a standard GoPro camera. So our design, as you can see in this picture, is just a GoPro camera mount connected to a ball joint, which is going to link to the ARM subsystem. This was our first design. We ran into a slight issue where we couldn't figure a good way to securely mount the GoPro camera mount to the plate. So we came up with this second design, which is two plates that are going to be formed around the GoPro mount that will be bolted together to securely hold it in place while the the ball joint you can see in red is connected to the ARM subsystem. Next slide, please. Now, the adjustability of the subsystem is shown in this video. You can imagine an astronaut holding the, if this microphone was a squeeze-release handle, one hand would be on that, and then his or her other hand would just maneuver the camera and therefore the ball joint pretty simply. And then when you release the squeeze-release handle, it'll lock in place, and that will be the final viewing angle. You can see the next slide, please. All right, so the camera mount subsystem is constrained within the bounds of three requirements, just like every other subsystem. It has pitch and yaw adjustability. It has 26.6 degrees of adjustability in its most limited axis on both sides. So that's going to be adding up greater than our 45-degree minimum. We meet that requirement. Next slide, please. The weight, we had it at about 1 pound for this subsystem. That's not including the GoPro camera, but the 1.5 pounds was our required limit, so we're still good there. Next slide, please. And then we have a base area because we didn't want to have too cumbersome of a design for the stored configuration. We limited ourselves to 5 square inches, and right now we're coming in at 4 square inches with our current design. So we also performed some stress analysis on this subsystem just to make sure that it would maintain that 20-pound force requirement. In this picture, we held the ball joint in place and applied a 20-pound force axially in the point most likely to fail, which was that cylindrical connection point between the ball and the plate. We are well within our requirements at about 7,000 PSI, whereas our limit was about 35,000 PSI. This next picture is a displacement graph using that same test. We see hardly, or as you can see, we don't have hardly any displacement. We're not really worried about slippage or anything, so we're good there as well. Slide. All right, I'm going to hand it off to Daniela to wrap it up.
Thank you, Sean. So Project CAM has experienced 2 significant lessons throughout the semester. The first lesson was understanding the requirements set by the competition and making sure that our interpretation is the same as the neutral buoyancy lab, and having those communications with them to make sure we implement those correctly into our design. The second lesson that we learned was making sure the communication between the different subsystems, as you can see with the system architecture, is clear, and that way our design is functioning properly. And we'd also like to take this time to acknowledge Dr. Martin, Professor Mangum, and Dr. Sensmeyer from the College of Engineering for supporting us throughout the semester, Dr. Betcher and Susie Roth from the Undergraduate Research Institute for helping us with our URI grant proposal, and Scott Ray from the Neutral Buoyancy Lab for helping us with our design. And in conclusion, Project CAM has met all our significant requirements for the Micro G Next competition, but we still look into adding further improvements into our design to be more competitive when we travel to the Neutral Buoyancy Lab. Any questions?
Okay, thank you. Good presentation. I really enjoyed that for a variety of reasons that I'll come on to. But can I just clarify something? You designed the handle. The astronaut sticks his bit on the top and moves the camera. Who built the arm? Did you guys? Are you guys designing and building the arm?
Yes, we designed each subsystem of the.
And is it all mechanical movement at the top?
Yes.
Okay. So, first statement then is don't underestimate the problems of an astronaut working A with stuff like that and B in 6 degrees of freedom because you've got 3 translation and 3 rotation. Have you tried talking to any astronauts, past or preferably past, about the difficulty of what they have actually working in space on stuff like this?
So after yesterday, we received more comments based on our design, feedback from the Neutral Buoyancy Lab, and we plan on talking to them further in our future mentor to be able to discuss those issues with making sure that an EVA hand could operate this. So we do plan on doing so, but we have not talked to anyone recently.
Well worth doing. The other thing that occurred to me as well when I was reading this stuff, and this is a really difficult problem, so congratulations on taking it on. The world experts in this stuff are MBA in Brampton, Ontario. You probably don't have time to start a dialogue with them, but at the very least, I suggest have a look on their website and all that stuff. You haven't said anything about risk. Have you done a risk analysis of what the main issues are that will stop this being successful?
So the main risks that we have taken into consideration so far are possible pinch points and making sure that any material on there will not damage any interfaces or damage the astronaut suit in anything whatsoever. And the only other test that we have done so far was making sure that if a 20-pound force, or if an astronaut decides to yank on it, if it's going to come apart, and currently we are safe in that aspect.
Okay. There's one big risk which you haven't mentioned there, and it's probably the biggest risk by far, which is why I suggest if you possibly can, have some sort of dialogue, even if through a third-party national, and that's the human risk, actually the astronaut. And let me give you very quickly an example. There are 2 cameras, 2 very, very high-resolution cameras on the space station at the moment. And I know that because my team in Oxford built them, and we haven't delivered it to NASA. Let me tell you what happened. They're pretty damn good cameras. I mean, they would be because we built them, and we built them cameras before. They went on a 4-hour spacewalk and installed them. And they switched them on, and nothing happened. And we thought, oh God, what's going on? And we couldn't figure it out. They then had to have a continuation, another 4 hours of taking the cameras off and taking them inside. As soon as they went back inside, they realised what the problem was. So we have cameras, cables through the skin of the space station, across these, by the way, were cosmonauts, so you all guys are safe, okay? They weren't astronauts. And then there's cables up to power supply. Do you know what the problem was? The cosmonauts, before they went outside, and these are very, very highly trained guys, had forgotten to plug it in. So here we are with millions upon millions. The spacewalk cost $2 million. The equipment cost $10 million. The cosmonauts are very bright guys, but they forgot to do something fundamental. And that's why you really do need to speak to somebody, somebody who has been in space doing an EVA, to see what the real problems are, because operating in zero gravity, when you're under huge stress anyway, about the safety of your own life, never mind the safety of the space station, it's a very, very difficult thing to do. You've got a great looking design which could be screwed by not taking the human component into account. So that's a really important thing to do. The other thing, of course, is just do a full risk analysis on everything else that can go wrong, even with your design. Okay.
Also, our hope-to-be mentor, Scott Ray, who I mentioned earlier, he teaches astronauts how to perform EVA missions at the Neutral Buoyancy Lab, so I can definitely ask him and get that input from him.
Sure. I mean, teachers know what they know.
Yeah,
Experience.
if he can.
It's nothing like actually talking to somebody who's been on them.
if he has.
All right, like to echo that you guys did a good job with the presentation. It's informative, and it was a different kind of problem. Haven't seen one of these before yet. So, I'm glad that you brought up that up, Richard, the human factor, because that is something we run into a whole lot is, well, it works perfect when used right. But then the second you hand it to an 18-year-old sailor and he bangs it around and uses it wrong, does it still work? And that's obviously with astronauts and cosmonauts, they're in theory better than that, but you're going to still face that challenge of, is it, when it's misused and abused, does it still work? In space, that can definitely be a problem, but it presents its own unique challenges. So I guess we'll start with the softball. What technical challenges did you guys learn about that you did not expect to encounter in this project? This is not a standard astronaut project.
I think the tube fault tolerance is where we were starting to get confused, or not confused, but it was a challenge for us, and the EVA operability, taking into account that you're not going to have the same grip strength, you're not going to have the same maneuverability with your hand and everything. I think that's where our biggest challenge was.
Okay. That's a good one. Human factors engineering is not easy. So it's not a bad thing. So another kind of just high level question too. If this were to be deployed in space, what would you guys change?
That's, NASA particularly said that they would handle that transition,
Okay.
but, so we have not taken that into account, but.
Okay, fair enough. Yeah, it's just one of those things that I'm wondering, are you guys thinking in that direction where, okay, yes, we work great underwater, but if we were to go out and actually go to space, what would we have to change? Okay. Yes, said they're gonna handle it. Go to slide 16. So, just a small comment on these kinds of slides. If you could show how you met the requirements. So, okay, you're under your 15-pound weight requirement. What is your weight? I know you guys said what the weights were, how you met it, but having it in writing helps me as the, I guess, panelist remember and look it up and flip back and forth and things like that. If you go to slide 25, please. This is really good that you showed us. Showing the different trade studies, just showing different mechanisms you considered. Only other thing I would add is if you could show pros and cons of each one. I think that'd be a worthwhile exercise. In something like this, particularly just because you're working with human factors, there's a lot of other things that me as an aerospace engineer I don't think about normally. Because normally I'm concerned about fire and structure. I'm not concerned about people having to grab onto it. So that would just be a good thing for me as an uninformed audience. I do have a question. You talked about interference between, I'm not sure what you call the part that grabs the handrail and the I-beams. Could you elaborate a little more on that?
I will let Ryan answer this question.
Sure, I'll just go ahead and go back to my slide if I can find it real quick. As you can see when the handrail or when the handle is depressed to open the system, the claws actually go into the truss frame itself, thereby preventing us from being able to get the ISS, the truss arms to actually connect to the truss. If our idea currently to fix this problem is to adjust those arms to a lower position onto those clamps, thank you. If we adjust this mounting location to a lower point on the claw, it will mitigate this interference from the claws actually hitting the truss frame. Does that answer your question?
Partially. I guess I'm wondering, so you plan to lower them? What do you mean by that? So does that mean raise in this picture or lower in this picture?
Lower in this picture.
Okay.
Current connection point is on this extrusion on the claw mechanism. That extrusion will actually get relocated to approximately this location on the claw, just to extend it past the reach of the claws when in an open position.
Okay. And have you done the calculations through to make sure that won't destroy your ability to grip other, I guess, interfaces, or lower your strength so that you you are deforming with the one. Sorry, I can't think of language.
Perfectly understandable. I've been tackling with the phrasing for this myself. We haven't done the calculations on the grip strength for the truss frame itself, or for the handrail or seated cart for that matter. We do have the math behind it, ready to calculate those strengths. But due to this issue, we're changing the geometry of the entire base subsystem itself, so that the spring pressure is going to adjust the mechanical advantage based off of the geometry that we have at the time. So once we get the interference taken care of, then we'll start doing the math and calculating the mechanical advantage and grip strength of each interface. And then from there go on to further adjust the design to maximize the mechanical advantage that we'll see.
Okay, fair enough. I was wondering how far down that change road you've gone. Because the concern I see with this in particular is you change one part, and you unintentionally change another, and another. You get into this endless cycle of, I gotta keep making changes. So I wanted to know if you guys had gotten to the point of, this is the one part we have to change, and that will affect all the other change, or allow for all the other changes. But it sounds like that's a little premature at this point. Just one other general comment. You guys could go ahead and show the budget and how many hours this is taking you. I think that'd just be a good practice to get into, so you guys can see this is what engineers cost, and they're very expensive. So it would just be a worthwhile exercise, I think. Overall, this is a good project. It's very interesting. It's something totally out of the box that I hadn't seen before. And I look forward to seeing you next semester.
Thank you.
Good job. I would just like to say that I really enjoy these backup slides where you actually put all the requirements, so that if we do feel like going back and looking, it's there for us. Especially since your presentation is a lot more graphic, or more graphics than those from some of the other classes. It's really nice to have the information back there. And have you guys started to actually prototype and build any of your cost system?
Not yet, but we plan to do so next semester before the intense building session to create a prototype through either 3D printing or just manufacturing to be able to test it.
Is NASA going to help you guys build the final product, or is that going to kind of rely on you?
We will have a mentor to guide us and give us more feedback and everything, but they will not be providing any financial help or anything.
I thought all of the gifts that you included of the CAD motion, that was all really good in describing how you're meeting the objectives. Since you were, a lot of it was kind of verbal, you were saying, oh, we want to make sure we can respond to these different things, and you had all the pictures to back up that you do that. I thought that was really good. It's a good way to really drive that point home. I think that is about all I have to say.
Thank you.
Are there any other questions from the audience? We got it. Go.
Just kind of, not really like a question, more kind of like a comment. Being in a CAD center myself, I noticed you guys were talking about units between newtons and pounds and everything. I would try to be very consistent. Just and assuming that the ISS is probably metric. Yeah, doing that myself, that killed us for a few weeks, having consistent units. So I would definitely go through, because you guys mentioned PSI and pounds and stuff for your analytic.
From our experience with NASA, they have not been consistent either. Their requirements document tends to switch around.
Yeah.
And Sean, you were saying about the ISS not being metric.
Oh yeah, so the measurements that were given to us, they were not given in any metric units. They were given in inch units that were to the 3rd or 4th decimal place. They were very odd units that were given to us, and so we were just basing all of those off of what was given to us, especially when designing the base subsystem. That was all taken into account using their numbers and everything. So they gave it to us in inches and pounds and everything like that. So the only things that were converted were things that we thought had to be absolutely necessary converted.
Yeah, just kind of things to look out for, just because I know having inconsistent units really can throw a bug in things.
Definitely, thank you.
And I got can you go to your last slide, your conclusion slide?
No, it's not. The requirements set by the MicroGNX challenge.
Okay, but, so when you use the word adhere, do you mean that you're designing towards those requirements, or you've satisfied those requirements, or?
Okay. The intent was that we satisfied all the requirements.
Okay, so my second question, if you've satisfied all your requirements on paper, why are you making improvements? Is there a mandate for that?
For the user safety, they want us to minimize all pinch points, minimize anything other like that, and we have seen after.
So there's a mandate for that?
Yeah.
Okay. Those.
Thank you.
Any other questions?
I'll just make a quick comment on the question before last, on units. You asked a very good question, and your answer was, well, yes, it is confusing. You've got to get that absolutely right. And if you don't know the story, look up the story of Mars Climate Observed in 1990. I don't know, how many people know the background to that? Everybody, okay, fine. Because that was a £2 billion mistake, just simply because of the screw up between it and so it's, and it was a human error. It wasn't a design engineering error. So you really do have to get that straight, and you've got to make. One of the things I teach when I talk about project management is problems often happen in the interfaces, more often than anywhere else. And the interface, if you're dealing with metric units, you better be damn sure that the person that's receiving your information knows their metric units, or zero, whichever it is, be consistent.
We'll definitely take that for going forward.
It won't cost you $1 billion if you get it wrong, but it may not work because you get it wrong.
Well, thank you guys. I think
Thank you, everybody.